work begins. We equip him and make him intake water just enough so that the tip of his cap emerges from the surface. At this point, his density is approximately equivalent to that of water. Then we find the volume of air bubble inside him to be 1.7 cube milliliters. The facility where his training takes place is a 1.5-liter Diet Coke bottle with a 10 milliliter syringe caught glued to the lid. We fill up the container of total volume 1510 milliliters with water and place Dave inside. Ready or not, here we go. As Dave slowly approaches the bottom of the bottle, we record the depth he arrives at and the volume of the container at several instants. That we measure his air bubble volume as well. We notice that as the plunger presses down from 10 to 6 on the syringe, Dave does not move at all. This indicates an error in the procedure to calibrate neutral buoyancy.
The science
Dave's
behind
density at the start of the dive is slightly smaller than water density.
to be consisting of the eyedropper and the air trapped inside. Pascal's law states that a pressure applied at any point on a confined incompressible fluid is transmitted equally throughout the fluid. When the container is pressurized due to a reduction of volume in the syringe, the pressure is passed on to Dave. Since air is more compressible relative to plastic and rubber, the materials that make up Dave's body, we can say that the pressure change is mostly reflected by the change in the volume of the air bubble, and not the eyedropper shell. According to the ideal gas law, PV equals nRT, everything on the right-hand side is constant in this case, leaving V inversely related to P. The reduction in the system's internal component volume, and the fact that all mass stays within the system at all times, leads to a decrease in the system's total density. According to Archimedes' principle, Dave begins to sink because his density exceeds that of water, and there isn't a large enough buoyancy to support him. We assume steady state at several instances where Dave seems to have stopped for a bit. Equilibrium means that the pressure experienced by the air bubble should equal the pressure exerted by the surrounding water. Since the air bubble pressure and the water pressure at the beginning of the experiment is unknown, our analysis would be based on their change in the measuring process. We denote the air bubble's pressure change using the ideal gas equation as nRT over volume change, and denote the water pressure change using rho g times the change in the vertical position. Then equate the two expressions. It can be inferred that delta H and delta V of air are in a linear relation since the other variables are all constant in this experiment. And now, time to talk numbers. Dave is dying to find out how much our results are consistent with the theoretical prediction. To begin with, it can be implied from Dave's constantly decreasing vertical position that, because we're only pushing down the plunger and not pulling it back up, Dave's density constantly increases beyond the limit for neutral buoyancy. Then, as we plot a regression of the vertical position with respect to 1 over air bubble volume, we notice that their change is indeed linearly correlated. We conducted our experiment using only tap water at room temperature. However, some may wonder how the properties of water, such as purity and temperature, would affect the results if they were to vary. We know that as temperature increases, water would become less dense. To reach neutral buoyancy in this scenario, we would need to have Dave intake less water and require less density. When salt is dissolved into water, the density of the mixture is larger than the density of water alone. Therefore, in order to make Dave's initial density equal to the liquid, we would need to have him intake more mass. The same laws behind Dave's diving practice are also applicable in fish physiology. Most bony fish have a swim bladder that models a lung and enables fish to control their buoyancy, or hiking the water column without swimming.